Welcome to Summarize Science. During the COVID-19 pandemic, we all heard about the R number, which told us how many people one sick person would infect on average. It was our key indicator for whether the pandemic was growing or shrinking. But this paper reveals how a unique feature of COVID-19 made calculating that number trickier and potentially more misleading than we thought. The core of the problem is something called presymptomatic transmission. Unlike the flu, people with COVID could be highly infectious for days before they ever showed symptoms. This creates a strange situation where an infected person might show symptoms after the person they infected does. This time between symptom onsets is called the serial interval, and for COVID-19, it could actually be a negative number. This graph of real-world data from an early outbreak shows this clearly. The bars represent infection pairs, and you can see a significant number of them fall on the negative side of the timeline. This is the statistical signature of presymptomatic spread, and it poses a big challenge for traditional disease models, which often can't handle negative time intervals. To get around this, scientists often use a simplified version of a formula to calculate the R number from a bell curve or Gaussian distribution of data. However, this paper argues that this common shortcut, shown here as equation 11, has a serious flaw. It consistently produces R numbers that are too low. The author proposes a more accurate method using the full formula, equation 10. The key insight is to add a realistic lower cutoff to the data. Essentially, you can't be infectious an infinite number of days before you get sick. There's a real-world limit determined by the virus's incubation period. By telling the model to ignore impossible negative values beyond this cutoff, the results become far more accurate. This graph of Germany's R number over 2 years shows just how much of a difference this makes. The author's more accurate method produces predictions, the horizontal bars, that line up well with the real-time data, the squiggly lines. The commonly used, simplified method would predict R numbers far lower, underestimating the true speed of the virus's spread. So, let's recap the important points. First, COVID's ability to spread before symptoms appear created a statistical puzzle for scientists. Second, a common mathematical shortcut used to solve this puzzle often underestimated how quickly the virus was actually spreading. Third, by applying a realistic limit based on the virus's incubation period, this paper shows how to get a much more accurate picture of the R number. What does this mean for the future? It provides a more robust tool for public health officials to analyze diseases that spread silently. Getting the R number right helps us react with the right interventions at the right time, a lesson that could be critical in the next pandemic. Thanks for watching Summarize Science.